Right now, as you watch this, there's a bomb ticking in the sky. Not a nuclear bomb, not an asteroid, something you can't see coming and can't hide from. A solar flare powerful enough to knock out every piece of technology on Earth in minutes. It's happened before, it will happen again, and when it does, modern civilization as we know it could collapse in hours. If understanding the invisible threat above us sounds important, a quick subscribe would mean the world to me, and drop a comment letting me know where you're watching from. Let's explore the explosion that's aiming at us right now. The sun looks calm from here, a steady ball of light in the sky, reliable, predictable, rising every morning and setting every evening. But that's an illusion created by distance. The sun is 93 million miles away. At that distance, almost anything would look calm. But up close, the sun is chaos, a roiling ball of plasma with temperatures reaching millions of degrees. Magnetic fields, twisting and tangling. Explosions constantly erupting from its surface that would dwarf anything on Earth. The entire planet Earth could fit inside some of the storms on the sun's surface. And these explosions, these solar flares, send radiation and charged particles screaming across the solar system at millions of miles per hour. When these particles hit Earth, they interact with our magnetic field. Usually, our magnetosphere protects us. It deflects most of the dangerous radiation, but a powerful enough solar flare can overwhelm these defenses. And when that happens, strange things occur. Beautiful things like auroras dancing across the sky at latitudes where they're never seen. But also dangerous things. Electrical systems overload, satellites fail, power grids collapse. In 1859, before we had the technology to be truly vulnerable, a massive solar flare struck Earth. It caused telegraph wires to catch fire. Operators received electric shocks. Some telegraph systems continued to work, even with their power sources disconnected because the flare itself was supplying electricity. The aurora was so bright that people in the Caribbean could read newspapers at midnight by its light. Imagine that. Standing in Cuba at midnight and reading a newspaper by the glow of the northern lights. That event is called the Carrington Event, named after the astronomer Richard Carrington, who observed the flare on the sun's surface. It remains the most powerful solar storm in recorded history. But here's the terrifying part. That happened in 1859, when the most advanced electrical technology was the telegraph, a simple system of wires and batteries. If the Carrington event happened today, the damage would be incomprehensible. We have built an entire civilization on technology that's vulnerable to solar flares, satellites that control everything from GPS to communications to banking, power grids with transformers that would melt under the electrical surge, internet infrastructure that would fail. Every plane in the sky would lose navigation. Every hospital would lose power. Every financial transaction would stop. Modern life would halt completely. And the recovery would take not days or weeks, but potentially years or decades. Let's understand what a solar flare actually is. The sun is not a solid object like Earth. It's a ball of plasma. Plasma is the fourth state of matter after solid, liquid, and gas. It's so hot that atoms break apart into electrons and nuclei. These charged particles move constantly, creating electrical currents, and electrical currents create magnetic fields. The sun's magnetic field is incredibly complex. It's not like Earth's simple north and south poles. The sun's magnetic field has thousands of loops and tangles, and these magnetic field lines store enormous amounts of energy. Sometimes, these field lines become so twisted and stressed that they snap, like a rubber band stretched too far. When they snap they release all that stored energy in an instant. This is a solar flare. The energy released is staggering. A large solar flare releases about 10 million times the energy of a volcanic eruption on Earth, or the equivalent of billions of nuclear bombs exploding simultaneously. This energy comes out as light across the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet light, X-rays, gamma rays, all released in a burst that lasts minutes to hours. The light reaches Earth in about 8 minutes because light travels at light speed. But light isn't the only thing released. The flare also accelerates charged particles, protons and electrons. These particles shoot out from the sun at incredible speeds. Some travel at a significant fraction of light speed. When billions of these particles stream toward Earth, it's called a solar energetic particle event. These particles take longer to arrive than the light, anywhere from minutes to hours depending on their speed. But they're far more dangerous to technology. And finally, sometimes a flare is accompanied by what's called a coronal mass ejection, or CME. This is when the sun literally throws a chunk of its atmosphere into space. Billions of tons of plasma ejected at speeds up to several million miles per hour. If this plasma cloud hits Earth, it compresses our magnetosphere and can cause geomagnetic storms that last for days. The key thing to understand is that solar flares are not rare. They happen all the time. The sun goes through an 11-year cycle of activity. At solar minimum, flares are relatively uncommon and weak. At solar maximum, they happen daily, multiple times per day sometimes. Most are small. They cause minor disruptions to radio communications or beautiful auroras, but nothing catastrophic. But occasionally, very occasionally, the sun produces a monster. A flare so powerful that it threatens everything we've built. These extreme events might happen once or twice per century. We've had one in recorded history, the Carrington event. We nearly had another in July 2012. That one missed Earth by about 9 days. If it had hit us, the consequences would have been devastating. So let's talk about what actually happened during the Carrington event to understand what we're dealing with. It began on September the 1st, 1859. Richard Carrington was an amateur astronomer who regularly observed the sun, projecting its image onto a screen because looking directly at the sun would blind you. On that morning, he was sketching sunspots when suddenly 2 brilliant white lights appeared on the sun's surface. They brightened rapidly, reached peak intensity, and then faded over about 5 minutes. Carrington knew immediately he was witnessing something unusual. He ran to fetch witnesses, but by the time he returned, the lights had dimmed. He recorded the observation carefully, making drawings and notes about the time and location. What Carrington saw was the flare itself, the initial burst of light and radiation. This light crossed the 93 million miles to Earth in 8 minutes. But The real damage came from what followed. Within 17 hours, faster than expected, the coronal mass ejection hit Earth's magnetic field. The impact was so powerful that it caused what's called a geomagnetic storm, the strongest one ever recorded. Earth's magnetosphere was compressed dramatically. Charged particles poured into the upper atmosphere, and this created electrical currents in the ground and in any conductors, including telegraph wires. Telegraph operators all over North America and Europe reported bizarre phenomena: sparks flying from telegraph equipment, paper catching fire, operators receiving electrical shocks when they touched their equipment. Some operators disconnected their batteries but found their systems still worked. The storm was inducing enough current in the wires to send messages without any power source. Messages were sent hundreds of miles using only the electricity from the solar storm. One operator in Boston disconnected his battery and managed to communicate with Portland, Maine for over 2 hours using only the storm's power. It was like the sky itself was powering the telegraph system, but the most spectacular effect was the aurora. Normally, auroras are confined to high latitudes near the Arctic and Antarctic circles. They're caused by charged particles from the sun colliding with gases in Earth's upper atmosphere, causing them to glow. During the Carrington event, the aurora was visible as far south as the Caribbean, in Cuba, in Hawaii, in Central America. People in the northeastern United States woke up at midnight thinking it was dawn because the sky was so bright. Gold miners in the Rocky Mountains woke up and started making breakfast, thinking morning had come. The light was red, green, purple, shifting and dancing across the entire sky. People who had never seen an aurora in their lives watched in wonder and fear. Some thought it was the end of the world. Some thought buildings were on fire. The light was bright enough to read a newspaper by. Scientists studied the event afterward and realized they had witnessed something unprecedented. But at the time, they didn't fully understand what had happened. The sun had somehow sent energy to Earth that disrupted the magnetic field and electrical systems. They couldn't explain the mechanism, and, more importantly, they couldn't predict when it might happen again. In 1859, the consequences were relatively minor. Some telegraph equipment was damaged, some wires needed to be replaced, but the telegraph was a simple technology. It could be repaired quickly. Operators could work around the disruptions. Life continued mostly normally. People didn't depend on the telegraph for survival. It was a convenience, a way to send messages quickly, but you could live without it. Now, let's jump forward to today. We are unimaginably more dependent on technology than anyone in 1859 could have imagined. Every aspect of modern life relies on electrical systems and electronics. Your phone, your computer, your car, traffic lights, hospital equipment, water pumps, sewage systems, refrigeration, heating, air conditioning, manufacturing, transportation, communications, banking, government, military. Everything runs on electricity and increasingly on satellite-based systems, and all of it is vulnerable to solar flares. Let's start with satellites because they're the most exposed. Satellites orbit above Earth's protective atmosphere. They're in the direct path of solar radiation and charged particles. During a solar storm, the radiation levels in space increase dramatically. This radiation can damage electronic components. It can cause single-event upsets where a charged particle hits a computer chip and flips a bit from 0 to 1 or vice versa. Usually, this just causes a minor glitch. The satellite's computer resets and continues working, but sometimes the damage is permanent. A key component fails and the satellite becomes useless. A piece of space junk tumbling uselessly in orbit. But there's another problem. During a solar storm, the upper atmosphere heats up and expands. This increases the air resistance that satellites experience. Normally, the atmosphere at satellite altitudes is so thin it barely matters. But during a storm, it becomes significant. Satellites slow down, their orbits decay. They have to use fuel to boost themselves back up to proper altitude, and if they run out of fuel, they fall. They burn up in the atmosphere or crash back to Earth. We've lost satellites this way. In recent decades, several satellites have been knocked out by solar storms. Some temporarily, some permanently. Now think about what we use satellites for. GPS navigation. Every smartphone, every car with navigation, every plane, every ship, every military operation. GPS relies on a constellation of satellites sending precise timing signals. Your GPS receiver calculates your position by measuring the time it takes for signals from multiple satellites to reach you. If those satellites are disrupted or their signals are distorted by a solar storm, GPS stops working. Suddenly, every plane in the sky loses precise navigation. Every ship at sea doesn't know exactly where it is. Every car's navigation system stops working. Delivery trucks get lost. Emergency services can't pinpoint locations. Military operations are blind. Communication satellites are another critical system. Internet traffic, phone calls, television broadcasts, weather forecasting, all rely on satellites. If a solar storm knocks out satellites, large portions of the internet go down. International communications fail. Weather forecasts become guesswork because weather satellites provide the data meteorologists use. We'd go back to predicting weather by looking at clouds and feeling the wind. Your phone might not work, not just for data but for voice calls too, because much of the cellular network routes through satellites at some point. The modern world depends on instant global communication. A solar storm can cut those connections in minutes, but satellites are just one vulnerability. The power grid is another, and this one is potentially catastrophic. The power grid is the system that generates electricity at power plants and distributes it to homes and businesses through high-voltage transmission lines. It's one of the most complex machines humans have ever built. Thousands of power plants, millions of miles of wire, transformers to step voltage up and down, control systems to balance supply and demand. And it all has to work perfectly every second of every day because electricity can't be stored in large quantities. It has to be used the instant it's generated. The power grid is vulnerable to solar flares because of the same effect that caused telegraph wires to spark in 1859. When a coronal mass ejection hits Earth, it distorts our magnetic field. This creates changing magnetic fields which induce electrical currents in any conductor, including power lines. These currents are called geomagnetically induced currents, or GICs. During a severe solar storm, GICs can be enormous, hundreds of amperes flowing through transmission lines. Now, the power grid is designed to handle certain amounts of excess current. Circuit breakers protect against overloads, but GICs are different. They're direct current, which is different from the alternating current the grid normally uses, and they can bypass safety systems. The most vulnerable components are transformers. These are the large units you see at power substations. They step voltage up for long-distance transmission and back down for local distribution. Transformers are expensive. A single large transformer can cost millions of dollars. And they're custom built. You can't just buy one off the shelf. If you order a replacement transformer today, it might take a year or more to manufacture and install. Each one is designed specifically for its location in the grid. They're huge. They weigh hundreds of tons. They have to be transported by special trucks and cranes. Installing one is a major engineering project. GICs can damage or destroy transformers. The direct current causes core saturation. The transformer overheats. Internal components melt. Insulation breaks down. If the transformer is pushed too hard for too long, it fails catastrophically. It burns out, and once it's destroyed, that part of the grid goes down. Power stops flowing to everything downstream of that transformer. Thousands or millions of people lose electricity instantly. And remember, replacing that transformer takes months or years. Now imagine this happening not to one transformer, but to dozens or hundreds simultaneously across a continent. A cascading failure where one transformer failing causes others to overload and fail. The entire grid could collapse. This is not theoretical. It's happened. On March 13, 1989, a solar storm caused a massive power outage in Quebec, Canada. The storm wasn't even as powerful as the Carrington event, but it was strong enough. The Quebec power grid collapsed in 90 seconds. 6 million people lost power, some for a few hours, some for days. The storm fried transformers, damaged equipment, caused surges that rippled through the grid. Quebec is particularly vulnerable because of its geography. The rock underneath Quebec is highly conductive. This makes GIC stronger in that region, but any power grid is vulnerable. The United States, Europe, Asia, anywhere with long transmission lines and transformers. A Carrington-level event today could knock out power grids across entire continents for months or years. Think about what that means. Months or years without electricity. No lights, no heating or cooling, no refrigeration, food spoils, no water pumps, so no running water, no sewage treatment, so sanitation fails, no gas pumps, so even if you have fuel in your car, you can't get more, no internet, no phones, no television, no radio. Hospitals lose power, life support equipment stops, surgery becomes impossible without light and monitoring equipment. Medications that need refrigeration spoil. People on dialysis die. People with pacemakers or other electronic medical implants are at risk if they need adjustments or replacement batteries. The death toll would be staggering. Not from the solar flare itself. That doesn't directly harm humans. We're protected by our atmosphere and magnetic field. But from the collapse of the infrastructure we depend on, supply chains break down immediately, grocery stores empty in days. Most stores only stock a few days' worth of inventory. They rely on constant deliveries. No electricity means no deliveries. Trucks can't fuel up. Refrigerated goods spoil. Within a week, food riots start. Within a month, mass starvation in cities. Urban areas can't feed themselves. They depend entirely on food being trucked in from rural areas. That system collapses without electricity and fuel. Rural areas might fare slightly better. They have more local food production, but they still depend on electricity for wells and irrigation. And they're not immune to the chaos. Law and order break down when people are desperate. When your family is hungry, you do what you have to do. Police can't respond to calls without working communications and vehicles. Hospitals can't treat the injured. Fires burn unchecked because fire departments can't pump water. In 1859, none of this mattered because society wasn't dependent on electricity. Today, electricity is the foundation of everything. Remove it, and modern civilization collapses almost instantly. This is the nightmare scenario, the thing that keeps emergency planners awake at night. A Carrington-level solar storm hitting Earth today, and we've come close, terrifyingly close. In July 2012, a massive coronal mass ejection erupted from the Sun. It was as powerful as the Carrington event, possibly more powerful. Scientists studying it afterward said it had the potential to cause catastrophic damage. Multiple trillions of dollars in economic losses, years of recovery time, millions of deaths from infrastructure failure. But we got lucky, incredibly lucky. The ejection happened when that part of the Sun was not facing Earth. It missed us by about 9 days. If it had happened 9 days earlier, when the Sun had rotated to point that region toward Earth, it would have hit us directly. We would have had about 17 hours warning, 17 hours to prepare for a disaster that would reshape civilization. What would we have done with 17 hours warning? Not much. You can't shut down the power grid safely in 17 hours. Even if you could, it would cause chaos. Imagine the announcement. The government says everyone will lose power indefinitely starting tonight. Panic would be immediate. People would rush to stores to buy supplies. Stores would empty in hours. Gas stations would run dry. Banks would be mobbed. Fights would break out. Accidents, looting. The breakdown of order before the storm even hit. And shutting down doesn't necessarily protect the infrastructure. GICs can damage equipment even if it's not actively transmitting power. The only real protection is to physically disconnect components, which takes time and planning. 17 hours is nowhere near enough, so we dodged a bullet in 2012. But it made scientists realize how vulnerable we are. They started studying the event intensely. What they found was alarming. The 2012 storm was one of the most powerful ever recorded. Its speed was exceptional. The coronal mass ejection was traveling at about 3,000 kilometers per second. That's over 6 million miles per hour. At that speed, it would have reached Earth in just 15 to 17 hours. And the magnetic field orientation was perfect for causing maximum damage. When a CME hits Earth, the orientation of its magnetic field matters. If it's aligned opposite to Earth's field, the two fields can reconnect and transfer enormous amounts of energy. This is what causes the worst geomagnetic storms. The 2012 event had exactly that alignment. If it had hit Earth, it would have been catastrophic. Scientists estimated that the economic damage from such an event could be $20 trillion or more. That's not a typo. 20 trillion. More than the entire annual GDP of the United States. And the recovery would take 4 to 10 years. A decade to rebuild infrastructure, replace transformers, restore power grids, get satellites back online. During that time, society would be fundamentally changed. We'd be living in a pre-electric world with a population that has no skills or preparation for that life. Most people today have no idea how to survive without electricity. We can't grow food, can't preserve food, can't cook without electricity or gas, can't find water or purify it, can't navigate without GPS, can't communicate without phones. We've become entirely dependent on systems that can be destroyed in minutes by a solar storm. The 2012 event also taught us something else. Space weather is not purely random. We can monitor it. We can see solar flares happening on the sun in real time. We have spacecraft positioned between the sun and Earth specifically to watch for CMEs. The SOHO spacecraft, the AC spacecraft, DSCOVR. These satellites watch the sun continuously. When they detect a CME heading toward Earth, they send warnings. This gives us lead time, usually less than a day, sometimes as little as 15 minutes for the fastest events. But it's something. It's better than being hit with no warning at all about the woos. Problem is that we don't have great systems in place to use that warning time effectively. Think about what would need to happen if we got a warning that a Carrington-level event was going to hit in 17 hours. First, the warning would have to be taken seriously. Space weather forecasters would need to convince government officials that the threat is real and imminent. This might be harder than it sounds. Officials deal with many threats. They have to prioritize. A solar storm doesn't sound as urgent as a terrorist attack or a natural disaster. It's abstract. People can't see it or feel it. It's easy to dismiss or delay action. But let's say the warning is taken seriously. What then? You'd need to coordinate responses across multiple countries. The power grid doesn't respect national boundaries. In North America, the grid is interconnected across the United States, Canada, and Mexico. A failure in one area can cascade to others. You'd need all three countries working together to protect the grid. Same in Europe, where power flows across dozens of countries. That coordination takes time. Phone calls, meetings, approvals. Even in an emergency, bureaucracy moves slowly. And you have 17 hours. Next, you'd need to start shutting down or protecting critical infrastructure. The power grid is the priority. But how do you safely shut down a power grid that serves hundreds of millions of people? You can't just flip a switch. Power plants have to be ramped down gradually. Wind and solar farms have to be disconnected. Nuclear plants have to enter safe shutdown procedures which take hours. The grid has to be balanced as you do this so you don't cause blackouts before the storm even arrives. And remember, shutting down the grid means hospitals lose power, life support fails, Patients die, so you can't shut everything down. You have to keep some systems running. But which ones? How do you decide who lives and who dies? Satellites need to be put into safe mode. This means shutting down non-essential systems, orienting solar panels away from the sun to reduce radiation exposure, reducing operational capacity to bare minimum. Airlines need to be notified to land planes or reroute away from polar regions where radiation is worst. Hospitals need to prepare for power outages, fire up backup generators, conserve fuel, discharge patients who can safely leave, stock up on supplies. Emergency services need to prepare for chaos. More police on the streets, firefighters on standby, ambulances fueled and ready. The military needs to secure critical facilities, protect against looting, maintain order, all in 17 hours. It's not enough time, and there's another problem. False alarms. Space weather prediction is not perfect. Sometimes a CME looks like it's going to hit Earth but misses. Sometimes it's weaker than expected. If you shut down the power grid and the storm doesn't hit or isn't that severe, you've caused a massive disruption for nothing. Billions of dollars in lost economic activity. Hospitals put at risk, planes grounded, chaos and panic, all unnecessary. After one or two false alarms, people stop taking the warnings seriously. The boy who cried wolf effect. When the real threat comes, no one acts because they've been burned before. This is a real challenge for space weather forecasting. How do you balance the need for caution with the consequences of false alarms? There's also the question of public communication. Do you tell people what's happening? If you announce that a solar storm is coming and might knock out power for months, panic is guaranteed. People will rush to stores. Gas stations will empty. Banks will see runs. Violence will break out. The social order could collapse before the storm even arrives. But if you don't tell people, they can't prepare. They're caught completely off guard when the power goes out. They have no supplies, no plan. They're more likely to panic later. It's a damned if you do, damned if you don't situation. There's no good answer. You have to balance transparency with stability. It's an impossible choice. So far, we've been lucky. The 2012 event missed us. Other large storms have happened when we've had more warning or when they've been weaker than feared. But our luck won't hold forever. Solar storms are a natural phenomenon. They're inevitable. The sun will produce another Carrington-level event. It's not a question of if, but when. And when it happens, we need to be ready. The question is, are we ready? The answer is no, not even close. Let's talk about some of the other near misses and actual impacts we've experienced. In October 2003, a series of powerful solar storms hit Earth. They were called the Halloween storms. These caused significant problems. Satellites were damaged, some permanently. The Japanese ADOS-2 satellite lost power and died. Swedish space weather spacecraft lost communications. Air traffic was disrupted. Airlines had to reroute flights away from polar regions because the increased radiation posed risks to crews and passengers. High-frequency radio communications failed across large parts of the planet. GPS systems showed errors. The power grid in Sweden experienced disturbances. South Africa lost power in parts of Johannesburg. These storms were not Carrington level. They were strong, but not catastrophic. And yet they still caused billions of dollars in damage and disruption. In January 2005, a solar storm caused anomalies in GPS satellites, positioning errors of up to 30 meters. That might not sound like much, but for precision applications, it's huge. Aircraft navigation, shipping, surveying, emergency services trying to locate people. 30 meters is the difference between finding someone and missing them. Some airlines reported navigation issues. Ships had to revert to traditional navigation methods. It was a reminder that even moderate solar storms can interfere with systems we depend on constantly. In December 2006, another solar storm disrupted satellite communications. Airlines lost contact with planes over the North Atlantic. For hours, pilots couldn't communicate with air traffic control. They flew blind, relying on backup systems and prearranged flight paths. No accidents resulted, but it was a close call. Modern air traffic depends on constant communication. Planes are spaced closely together to maximize efficiency. If you can't talk to them, if you don't know exactly where they are, the risk of collision increases dramatically. The 2006 storm showed how vulnerable aviation is to space weather. In March 2012, just a few months before the big one that missed us, a smaller solar storm caused disruptions. Delta Airlines had to reroute flights. GPS systems showed errors. High-frequency radio communications were disrupted. Again, billions of dollars in economic impact. Delays, cancellations, lost productivity. And this was a relatively minor event. Nothing like the Carrington event. Nothing like the July 2012 event that missed us. Just a moderate storm, but still enough to disrupt modern life in noticeable ways. These events are warnings. They're telling us that our technological civilization is fragile, that we've built systems without adequate protection against natural phenomena we've known about for over a century. We've prioritized efficiency and cost reduction over resilience and redundancy. The power grid operates close to capacity most of the time. There's little excess. If something fails, the system struggles to compensate. Transformers are expensive, so utilities don't keep many spares on hand. If one fails, they have to order a replacement and wait months for delivery. This works fine in peacetime with isolated failures, but it's completely inadequate for a disaster scenario where dozens or hundreds of transformers fail. Simultaneously, satellites are similar. They're built to be as light and cheap as possible. Weight is expensive in space. Every kilogram costs thousands of dollars to launch. So engineers strip out everything non-essential. Redundancy is minimized. Protection against radiation is limited to what's absolutely necessary. This works most of the time. Satellites operate for years without major problems, but when a big solar storm hits, they're vulnerable. Some fail partially, some fail completely. Some can be recovered by rebooting or switching to backup systems. Others are lost permanently, and replacing a satellite takes years. You have to build a new one, launch it, position it, test it. It's not like swapping a battery in a flashlight. You can't just pop in a replacement and move on. Our entire modern infrastructure is built on the assumption that disasters won't happen, or if they do, they'll be localized and manageable. A power plant fails. Okay, there are others to pick up the slack. A satellite dies. That's fine. There are redundant satellites. A transformer blows. No problem, we'll route power around it until we can replace it. This works for normal failures. Random equipment breakdowns, local disasters like hurricanes or earthquakes. But it doesn't work for a global event that damages everything simultaneously. If hundreds of transformers fail at once, there are no spares. If dozens of satellites are knocked out together, there's no redundancy. If the entire power grid collapses, there's no outside help because everyone is affected. This is what makes solar flares so dangerous. They're not localized. A Carrington-level event affects the entire day side of Earth, half the planet, everyone who happens to be facing the sun when the CME hits. And because Earth rotates, the effects spread. As different parts of the planet rotate into the day side, they get hit too. Within 24 hours, the entire planet has been exposed. Every power grid, every satellite, every piece of electronics, all vulnerable, all potentially damaged, and there's no safe place to retreat to, no unaffected region that can send help. We're all in it together, sink or swim as a global civilization. Now, you might be thinking, surely there are protections we can build. Surely engineers and scientists have thought about this and developed solutions. And you'd be partly right. There are protections, but they're expensive and not widely implemented. The most effective protection for electronics is something called a Faraday cage. It's an enclosure made of conductive material that blocks electromagnetic fields. If you put electronics inside a Faraday cage, they're protected from external electromagnetic pulses. The cage conducts the energy around the outside, not through the inside. Military facilities have Faraday cages protecting critical equipment. Some data centers do too, but most infrastructure doesn't. It's too expensive. A Faraday cage for a transformer would be massive and cost prohibitive. You'd need to build one for every transformer in the grid, thousands of them. No one wants to pay for that when the threat seems abstract and distant. There are also surge protectors and circuit breakers designed to handle power surges. Every home has them, but the kind of surge you get from a geomagnetic storm is different. It's direct current. It's long-lasting. It can overwhelm standard protections. You need specialized equipment designed specifically to handle GICs. Some utilities have installed this equipment at critical nodes in their grids, but not everywhere, not enough. It's a patchwork protection that might help in a moderate storm, but would be insufficient in a Carrington-level event. Satellites can be hardened against radiation. They can have extra shielding, redundant systems, radiation-tolerant components. Military satellites and some critical scientific satellites have these protections. But commercial satellites often don't. They're built to a budget. Extra protection means extra weight, which means higher launch costs. It's a calculated risk. The probability of a major solar storm during the satellite's operational life is low, so companies gamble. They save money by building lighter, cheaper satellites. Most of the time, they win the gamble. But when a big storm hits, they lose. And we all lose. because those satellites provide services we depend on. There's another aspect of solar flares we haven't fully discussed yet: the radiation itself. When a solar flare erupts, it releases radiation across the electromagnetic spectrum. Most of this radiation is harmless to us on the ground. Earth's atmosphere absorbs it. But for astronauts in space, it's a serious hazard. On the International Space Station, astronauts have to take shelter during major solar storms. They retreat to the most shielded parts of the station, areas surrounded by supplies and equipment that can block some radiation. They wait out the storm, monitoring their exposure levels. Too much radiation causes radiation sickness, nausea, fatigue, in extreme cases, death. Astronauts on the ISS are relatively protected because the station is in low Earth orbit, still within the outer edges of Earth's magnetosphere. But future astronauts going to the Moon or Mars will be much more exposed. They'll be outside the protective bubble of Earth's magnetic field. A major solar storm during a Mars mission could be fatal. This is a real problem for space exploration. We want to send humans back to the Moon. We want to send people to Mars. But the journey takes months. You can't predict solar activity months in advance. The sun could be quiet when you launch and erupt violently while you're en route. There's no way to turn around, no way to escape. You're stuck in your spacecraft with whatever radiation shielding you brought. Engineers are working on solutions: better shielding, safe rooms with extra protection, early warning systems. But it's a hard problem. Adding shielding adds weight. Weight makes missions more expensive. You have to balance protection with practicality. It's another calculated risk. How much danger are we willing to accept to explore space? Back on Earth, the radiation from solar flares affects airline crews and passengers, especially on polar routes. The Earth's magnetic field is weakest near the poles. It funnels radiation down toward the surface. During a solar storm, radiation levels increase dramatically at high latitudes. Flights over the Arctic or Antarctic experience higher radiation doses. For occasional travelers, this isn't a big concern. The dose is small, but for airline crews who fly these routes regularly, it adds up. They're exposed to more radiation than most people. Some studies suggest this increases cancer risk. Airlines monitor space weather and reroute flights during major storms to avoid the worst radiation. But this adds time and fuel costs. A flight from New York to Tokyo might normally fly over the North Pole because it's the shortest route. But during a solar storm, it has to detour south, adding hours to the flight time and burning more fuel. Multiply this across all polar flights during a storm, and the economic cost is significant. There's also concern about radiation effects on aircraft electronics. Modern planes are full of computers and sensors, navigation systems, autopilot, engine controls, all vulnerable to radiation. Usually, they're adequately shielded, but during intense solar storms, there's a risk of malfunctions. A computer glitch at the wrong moment could be catastrophic. Aviation authorities take this seriously. They issue warnings to airlines when major solar storms are expected. They recommend altitude changes, flying lower where the atmosphere provides more shielding, or route changes to avoid the worst radiation. Most of the time, it's just a precaution. Nothing happens. But occasionally, planes report strange instrument readings, or minor malfunctions during storms. It's a reminder that even at ground level or low altitudes, we're not completely safe from space weather. Let's think about the human element of all this, the psychological impact of a major solar storm. Imagine you wake up one morning and the power is out. That's not unusual. Power outages happen. You assume it'll be back on in a few hours, but hours pass and nothing. You try your phone, no signal. You turn on a battery-powered radio. Emergency broadcasts say the power grid has failed. No estimate for restoration. Stay in your homes. Conserve supplies. That's when the panic sets in. How long will this last? Days? Weeks? Do you have enough food? Enough water? What about medication if you need it? What if there's an emergency and you need an ambulance? You go outside. Neighbors are gathering, confused, scared. No one knows what's happening or what to do. Someone says it's a solar storm. That means satellites are down. 2. No GPS, no internet, no way to get information beyond local radio if it's still broadcasting. You can't call relatives in other cities. You don't know if they're okay. You don't know if this is just your city or the whole country or the whole world. The uncertainty is terrifying. Rumors spread. Some people say it'll be fixed in a day. Others say weeks. Someone claims the government is hiding the truth. Conspiracy theories flourish in information vacuums. After a day or two, stores run out of food. People who didn't prepare are desperate. Lines form at grocery stores, but there's nothing to buy. Trucks aren't delivering because gas stations don't have power to pump fuel. You can see the fuel in the underground tanks but can't get it out. People start hoarding. Fighting breaks out. The police try to maintain order, but they're overwhelmed. They're also scared for their families. Some officers abandon their posts to go home and protect their own. The thin veneer of civilization starts to crack. Water stops flowing because pumps need electricity. If you have a well, you can't pump it. If you're on city water, the treatment plants are offline. Sewage systems back up. Sanitation becomes a problem. Diseases spread. Hospitals are overwhelmed. They're operating on backup generators, but fuel is running low. Patients who need dialysis or other regular treatments can't get them. People die from preventable causes. Not because medicine doesn't exist, but because the infrastructure to deliver it has failed. The social fabric unravels as people revert to survival mode. Communities that were peaceful and orderly become dangerous. The strong prey on the weak. It's not that humans are inherently evil. It's that desperate people do desperate things. When your child is hungry, you'll steal food. When someone threatens you, you defend yourself. Violence escalates. Society breaks down. This is the nightmare scenario that keeps emergency planners awake, not the solar storm itself. That's just physics, radiation, and magnetic fields. The real disaster is what happens to human society when the infrastructure fails. We're not prepared psychologically or practically for a return to pre-industrial life. Most people have never lived without electricity. They don't know how to find water, purify it, grow food, preserve food, build shelter, make fire, navigate by stars. Skills our ancestors took for granted are lost. We're specialists in our modern economy. You might be good at accounting or computer programming or teaching, but Those skills don't help when the power is out. You need practical survival skills, and most people don't have them. Even people who consider themselves preppers, people who stockpile supplies and have plans for disasters, most are not prepared for a years-long grid-down scenario. They might have food and water for weeks or months. They might have generators and fuel, but years? No one has that much fuel. No one has that much food stored unless they're actively farming. And farming takes knowledge and time. You can't just throw seeds in the ground and expect crops. You need to know what grows in your climate, when to plant, how to deal with pests, how to harvest and preserve. It's hard work, and the learning curve is steep. People who try to start farming after a disaster hits will mostly fail, especially the first season. By the time they figure it out, they might have starved. There's also the question of security. If you have supplies and others don't, you become a target. People will try to take what you have. You need to defend yourself and your family. This means weapons. It means willingness to use violence. It means staying awake at night on guard duty. It's exhausting and demoralizing. Communities might band together for mutual protection and resource sharing. That's the best case scenario. People cooperating, pooling skills and supplies, working together to survive. But that requires trust. It requires leadership. It requires people putting aside their differences and focusing on survival. In some places, that will happen. In others, it won't. Communities will fracture along existing fault lines: race, religion, class, politics. Old grudges resurface, new conflicts emerge. It gets ugly fast. All of this from a solar flare, a natural phenomenon, not an enemy attack, not a deliberate disaster, just the sun doing what the sun does. It's humbling and terrifying to realize how fragile our civilization is, how dependent we are on systems that can be destroyed by something we can't control or prevent. We can't stop the sun from erupting. We can't deflect a CME. We're at the mercy of space weather. All we can do is prepare as best we can, build resilient systems, stockpile supplies, develop emergency plans, educate people about the risks, and hope we get lucky. Hope that when the next big one comes, we're ready, or at least as ready as we can be. Scientists are working on better prediction models. They're studying the sun in incredible detail. Solar observatories watch the sun 24/7. They track sunspots because sunspots are where flares originate. They measure magnetic field strengths. They look for signs that a large flare is building. Computers analyze the data, looking for patterns that precede major eruptions. Machine learning algorithms are being trained on decades of solar data to predict when and where the next big flare will occur. The goal is to give more warning time. If we could predict a Carrington-level event days in advance instead of hours, it would make a huge difference. We could evacuate populations, shut down grids safely, move satellites to safe orbits, prepare hospitals and emergency services. With enough warning, a disaster becomes manageable. Without warning, it's catastrophic. But prediction is hard. The sun is chaotic, turbulent. Magnetic fields twist in ways that are hard to model. Sometimes a sunspot looks dangerous but produces nothing. Other times, a relatively quiet region suddenly erupts with a massive flare. We're getting better at prediction, but we're not there yet. We can say with confidence that solar maximum is a riskier time than solar minimum. We can identify active regions that bear watching, but predicting the exact timing and magnitude of a specific flare days in advance, we can't do that reliably yet. Maybe we will someday. Progress is being made. But for now, we mostly get short-term warnings. The flare has happened. The CME has been launched. It's on its way. You have hours to prepare, not days. Hours, that's the reality we live with. There are international efforts to improve space weather forecasting and response. The United Nations has a working group on space weather. Countries share data from their solar observatories. There are protocols for warning systems. When one country detects a major event, they notify others. In theory, this allows coordinated responses. In practice, coordination is messy. Different countries have different priorities, different levels of vulnerability, different resources. A solar storm that's catastrophic for high-tech countries might barely affect less developed nations. They have less to lose because they're less dependent on vulnerable infrastructure. They might even benefit if wealthy countries are knocked back to their level temporarily. There's not a lot of incentive for them to invest heavily in space weather protection. It's a global problem, but the burdens and benefits aren't evenly distributed. The economic incentives are also problematic. Companies and utilities don't want to spend money protecting against a threat that might not materialize for decades. Their planning horizons are measured in quarters and years, not decades. Shareholders want profits now, not resilience against some hypothetical future disaster. Regulators can mandate certain protections, but regulations are often weak and poorly enforced, especially when compliance is expensive. It's a classic tragedy of the commons. Everyone benefits from a protected infrastructure, but no one wants to pay for it. So we remain vulnerable. We know the threat exists. We know it's serious. But we're not acting with the urgency the situation demands. History offers some perspective here. Major disasters often catch societies unprepared, even when the warning signs were clear. The levees in New Orleans. Engineers warned for years that they couldn't withstand a major hurricane. The warnings were ignored because repairs were expensive. Then Hurricane Katrina hit in 2005 and the levees failed. The city flooded. Over 1,000 people died, billions in damage, all preventable if the warnings had been heeded. Fukushima nuclear disaster in Japan, 2011. The plant was built to withstand tsunamis, but not tsunamis as large as the one that hit. Engineers knew larger tsunamis were possible. Historical records documented them, but the plant was built to a lower standard because higher protections would have cost more. When the big tsunami came, the plant flooded. Reactors melted down, radiation leaked. A vast area was contaminated, preventable if the warnings had been heeded. The pattern repeats. Warnings are issued. Experts say something needs to be done, but action requires money and political will. If the disaster is far in the future or probabilistic, it's easy to delay. There are always more immediate concerns, more pressing problems. So nothing gets done until disaster strikes. Then everyone asks why we weren't prepared. why we didn't listen to the experts. The same pattern will likely play out with solar storms. We have warnings now. Scientists are saying we're vulnerable. Engineers can design protections, but implementing them requires massive investment. Trillions of dollars globally to harden the power grid, to harden satellites, to build redundancy and resilience. That money won't be spent until after a disaster proves the threat is real. And by then, it's too late. We'll be dealing with the aftermath instead of prevention. The good news, if there is any, is that solar flares are not extinction events. They don't directly kill people. They don't destroy cities. They don't render the planet uninhabitable. Earth has been hit by solar storms for billions of years. Life has survived. Our ancestors lived through solar storms without even knowing they were happening. The storms are only dangerous because of the infrastructure we've built, the technology we depend on. If we lost that technology, life would be hard. Many people would die from the collapse of support systems. But humanity would survive. Eventually, we'd rebuild. It would take decades, but we'd recover. This is different from asteroid impacts or supervolcano eruptions or nuclear war. Those can cause extinction. Solar storms can't. They're a civilization-level threat, not a species-level threat. That's a meaningful distinction. We can survive them. We just need to be smart about preparation and response. There are also degrees of impact. Not every solar storm is a Carrington event. Most are much weaker. They cause minor disruptions. Some flickering lights, some satellite glitches, GPS errors, radio interference. Nothing catastrophic. Even fairly strong storms usually only cause localized problems. A regional power outage, some satellites offline, aviation delays. Expensive and annoying but manageable. It's only the extreme events that threaten civilization, and those are rare. We've had one confirmed Carrington-level event in recorded history. Maybe one or two others we don't have good records for. They happen perhaps once or twice per century on average. That's a low probability in any given year, but over decades, the probability accumulates. If you live 70 years, you have maybe a 50% chance of experiencing one. Those aren't terrible odds individually, but for civilization as a whole, it's a certainty. It will happen. The question is when, and will we be ready? We're currently in solar cycle 25, the sun's 11-year cycle of activity. We're approaching solar maximum, which is expected around 2025. This means the next few years are higher risk. More sunspots, more flares, more CMEs. Nothing to panic about. Most solar maximums pass without incident, but statistically, the risk is elevated. Space weather forecasters are watching carefully, monitoring every active region on the sun, ready to issue warnings if something big erupts. Meanwhile, the rest of us go about our lives, using our phones and computers, trusting that the power will stay on, assuming tomorrow will be like today. It's a reasonable assumption most of the time, but not always. Sometimes tomorrow is very different. Sometimes the world changes in ways we don't expect. A solar storm is one way that could happen, not the only way, but a real possibility. One we should be aware of and prepared for, even if we hope it never comes. The internet is another critical vulnerability we need to understand. When most people think about the internet, They imagine something abstract, data floating through the air, but the internet has a physical infrastructure. Cables, servers, routers, data centers, all vulnerable to solar storms in different ways. The backbone of the internet is a network of fiber optic cables. Many run underground or underwater. Fiber optic cables themselves are not directly affected by electromagnetic pulses because they transmit data as light, not electricity. But the equipment at each end of those cables, the routers and switches and servers, those are electronic and vulnerable. If a solar storm knocks out power to data centers, the internet goes down even if the cables are fine. Undersea cables are particularly interesting. There are hundreds of fiber optic cables lying on the ocean floor, connecting continents. All international internet traffic flows through these cables. Email from New York to London, video calls from Tokyo to Sydney, banking transactions from Singapore to Frankfurt. Everything goes through undersea cables. These cables are designed to be reliable. They're armored against damage from ship anchors and fishing nets. They have multiple redundant paths, so if one cable fails, traffic routes through others. But they're powered by equipment on land, amplifiers and repeaters along the cable route that boost the signal. Power stations at the cable landing sites. If solar storms knock out power to these systems, the cables go dark. International communication stops. The internet becomes fragmented. Countries or continents isolated from each other. You might be able to access local websites, but nothing international. Data centers are concentrated points of vulnerability. A data center is a warehouse full of servers. Thousands of computers running constantly, storing data and running applications. Everything from social media to email to banking to cloud storage, all housed in these facilities. They consume enormous amounts of electricity to run the servers and to cool them because computers generate heat. A typical large data center might use as much electricity as a small city. If the power grid fails, data centers have backup generators. But those generators need fuel, diesel or natural gas, and fuel supplies are limited. Maybe a few days' worth, maybe a week if they're well prepared. After that, the generators run dry, the servers shut down. Everything stored on those servers becomes inaccessible. Everything running on those servers stops. If the power outage lasts weeks or months, the data might be lost entirely. Hard drives degrade without power. Solid-state drives lose data over time without electricity to maintain the charge states. Think about what's stored in data centers. Your emails, your photos, your documents, your financial records, your medical records, business databases, government records, scientific data, historical archives. So much of modern life exists only as data on servers. If those servers go down permanently, that data is gone. This is different from past disasters. A flood might destroy a library, but the books exist elsewhere. Copies in other libraries, original manuscripts. Fire might destroy a building, but records exist elsewhere. With digital data, often there's only one copy, or maybe a backup in another data center. But if both locations lose power, both copies are lost. There's no paper trail, no physical artifact, just lost bits, unrecoverable. Some critical services have robust backup systems. Banks, for instance, keep offline backups of transaction records. They can reconstruct accounts even if the primary systems fail. But many services don't. Social media companies don't keep offline backups of your posts. Why would they? The data exists on redundant servers in multiple data centers. That's supposed to be enough. Cloud storage. Services might have backups, but those backups are also digital, stored on servers requiring power. If everything goes down simultaneously, the backups are inaccessible too. This is a modern vulnerability we haven't fully reckoned with. Our collective memory, our records, our data, all dependent on continuous electricity. Remove that electricity for long enough and it all evaporates. Aviation is critically dependent on systems vulnerable to solar storms. Modern planes are essentially flying computers. The engines are controlled by computers. Navigation is computerized. Autopilot. Communications. Everything. Pilots are trained to fly manually if systems fail, but modern planes are designed around the assumption that systems won't fail. Some can barely be flown manually. The computer systems handle so much of the moment-to-moment operation that human pilots would struggle to take over completely. And even if pilots can fly the planes manually, they need navigation information. Where are we? Where are we going? What's our altitude? What's our speed? Without instruments, you're guessing. Visual flight is possible during the day in good weather if you know the terrain. But at night, or in clouds, or over the ocean, you're lost without instruments. The bigger problem is air traffic control. Thousands of planes are in the air at any moment. They need to be tracked. Their positions need to be known. Their flight paths need to be coordinated to avoid collisions. This all depends on radar and communications. Ground-based radar shows air traffic controllers where planes are. Pilots communicate with controllers by radio to receive instructions. GPS supplements this, giving precise positions. If solar storms disrupt these systems, air traffic control becomes impossible. You can't see where planes are. You can't talk to pilots. You can't coordinate traffic. The safe thing to do is ground all planes immediately. Tell everyone to land at the nearest airport, but even that requires communication. And what if airports are already crowded? What if some airports have lost power and can't accommodate more planes? In 2006, a solar storm disrupted high-frequency radio communications over the North Atlantic. This is one of the busiest air routes in the world. Hundreds of flights per day between North America and Europe. For hours, pilots couldn't communicate with air traffic control. They followed pre-planned routes and hoped for the best. No collisions occurred, but it was luck. If two planes had been on converging paths, no one would have known until it was too late. The event highlighted how vulnerable aviation is, and that was a relatively minor storm. A Carrington-level event would be far worse. GPS could fail, radar could fail, radio communications could fail, all simultaneously. Every plane in the sky would be flying blind. The only safe option is to land immediately, but coordinating that without communications is nearly impossible. Pilots would have to make decisions independently. Land at the nearest airport, hope there's room, hope there's no other plane on the same approach. It would be chaos. Then consider what happens on the ground. Airports need electricity for everything: runway lights, terminal lights, baggage handling, fueling systems, air conditioning in the terminals, security screening. If the power goes out, airports shut down. No flights can take off. Flights arriving have to divert elsewhere. But if the power outage is widespread, there is no elsewhere. Every airport is dark. Planes running low on fuel have nowhere to land safely. Pilots have to attempt landings without runway lights, using emergency power if the plane has it, relying on training and skill and luck. Some would make it, others wouldn't. The death toll would be substantial. Financial systems are another critical infrastructure entirely dependent on electricity and electronics. Money today is mostly digital, numbers in databases. Your bank account is not a pile of cash in a vault. It's an entry in a computer. When you get paid, your employer's bank sends a digital message to your bank saying your account should increase by a certain amount. Your bank updates its database. Numbers change. No physical money moves. When you buy something with a credit card, another digital message. Your account decreases. The merchant's account increases. Banks reconcile these transactions constantly. Billions of transactions per day globally, all tracked electronically. If the power grid fails and data centers go down, financial records become inaccessible. You can't check your bank balance. You can't transfer money. You can't pay for things with cards because the payment processing networks are offline. ATMs don't work. Even if they have power, they can't communicate with banks to verify transactions. The entire electronic payment system collapses. We revert to cash, but most people don't carry much cash. In many countries, cash is becoming rare. People pay for everything with cards or phones. If those systems fail, how do you buy food? How do you pay for fuel? How do you pay rent? The economy freezes. Businesses can't operate without payment systems. Supply chains halt. Distribution stops. Shelves empty. Stock markets shut down immediately if the infrastructure fails. Trading is entirely electronic. Computers match buy and sell orders. High-frequency trading algorithms execute thousands of trades per second. All automated, all dependent on continuous power and communications. If the systems go down, trading stops. This might sound like a minor issue compared to people not having food or water, but the economic consequences are profound. Wealth is stored in stocks and bonds, retirement accounts, pension funds, investment portfolios. If the markets are closed for weeks or months, that wealth is frozen. You can't access it. You can't sell stocks to raise cash. If you're retired and living on investment income, you have no income. If you have a medical emergency and need to liquidate assets to pay for treatment, you can't. The wealth exists in theory, but you can't use it. And there's another problem. Uncertainty and fear cause market crashes. If the power grid fails and people know it's from a solar storm, they'll panic. When the markets reopen, everyone tries to sell. Sell everything. Get out. Cash out while you can. This overwhelms the system. Prices crash. Markets go into freefall. Circuit breakers are supposed to halt trading if prices drop too fast, giving people time to calm down. But in a true panic, circuit breakers just delay the inevitable. When trading resumes, the selling continues. Fortunes are lost, retirement savings evaporate, pension funds become insolvent. The economic damage extends for years even after the power is restored. The physical infrastructure might recover, but the financial infrastructure takes much longer. Medical technology is perhaps the most immediately life-threatening vulnerability. Hospitals depend entirely on electricity. Operating rooms need bright lights. Surgical equipment is powered. Monitors track patients' vital signs. Life support machines keep critically ill patients alive. Ventilators add for patients who can't breathe on their own. Dialysis machines clean blood for patients with kidney failure. Infusion pumps deliver medications precisely. Imaging equipment like X-rays and MRIs diagnose conditions. All of it needs electricity. Hospitals have backup generators for exactly this reason. Power outages happen, storms, equipment failures. Hospitals can't go dark. Lives are at stake. So they have generators that start automatically when the main power fails. But generators need fuel. A hospital might have enough fuel for a few days of operation, maybe a week if they conserve. They shut down non-essential systems, cancel elective surgeries, discharge patients who can safely leave, focus resources on keeping critical patients alive. But if the power outage lasts longer than their fuel supplies, they have a terrible choice: who lives and who dies. Patients on life support, patients in ICU, babies in neonatal intensive care. You can't save everyone. You have to choose. Triage. The patients most likely to survive get priority. The rest are made comfortable. It's a nightmare scenario that doctors dread. And all of this from a solar storm, a natural event, no one's fault, just bad luck and inadequate preparation. There are also patients who depend on medical devices at home, CPAP machines for sleep apnea, oxygen concentrators for respiratory conditions, home dialysis, powered wheelchairs. If the power goes out, these devices stop working. People die in their homes because the electricity they depend on is gone. Some might make it to hospitals, but hospitals are overwhelmed. They can't accommodate everyone. They're barely keeping their own patients alive. People who would survive with power die without it. The death toll mounts not from violence or starvation, but from the simple absence of electricity. This is unique to modern civilization. We've built life support systems for millions of people. Systems that work wonderfully when the power is on. But when it's not, those people are in immediate danger. The Quebec blackout of 1989 offers a preview of what could happen, but on a much smaller scale. On March 13th, a geomagnetic storm hit Earth. It wasn't Carrington level. It was strong but not unprecedented. The storm caused aurora visible as far south as Texas. Beautiful lights in the sky. But in Quebec, it caused disaster. The power grid serving 6 million people collapsed in 90 seconds. The storm induced massive currents in the transmission lines. A key transformer at the James Bay Power Complex failed. Without that transformer, power couldn't flow from the hydroelectric dams to the cities. Other transformers tried to compensate. They overloaded. Safety. Systems shut them down to prevent damage. The cascade happened so fast that operators couldn't react. One moment everything was fine. 90 seconds later, the entire province was dark. Most people got power back within a few hours. The grid was restarted section by section. But some areas were without power for days. Schools closed. Businesses shut down. People couldn't heat their homes. March in Quebec is cold, snow on the ground, temperatures below freezing. Without heat, homes became dangerous. Pipes froze. People bundled up and waited. Emergency shelters opened for those who couldn't stay in their homes. It was manageable because it was temporary, inconvenient and uncomfortable, but not catastrophic. The power came back. Life returned to normal, but it could have been much worse. If the transformers had been destroyed instead of just shut down, repairs would have taken months. If it had been winter instead of early spring, the cold would have been deadly. If the outage Hissy had affected food distribution, supplies would have run out. Quebec got lucky. The storm was strong enough to collapse the grid, but not strong enough to cause permanent damage. And it happened at a time of year when people could survive a few days without power. The lesson from Quebec is that our power grids are vulnerable. They're not designed to handle the stresses that geomagnetic storms create. Since 1989, some utilities have implemented protections, better monitoring of space weather, procedures for shutting down equipment if a major storm is forecast, installing devices that can block geomagnetically induced currents. But these protections are not universal. Some regions have them, others don't. It's a patchwork. And even the protections we have are designed for storms like the one in '89. They might not be sufficient for a Carrington-level event. We won't know until it happens. And by then, it's too late to add more protections. You work with what you have. You hope it's enough. You prepare for the worst and hope for the best. We do have systems for predicting and warning about solar storms. Space weather forecasting has improved dramatically since the Carrington event. We have satellites watching the sun constantly. SOHO, SDO, stereo. These spacecraft monitor solar activity. They see flares as they happen. They detect coronal mass ejections as they leave the sun. They measure the speed and direction of the ejection. They estimate when it will reach Earth and how strong the impact will be. This information is analyzed by space weather forecasters at organizations like NOAA's Space Weather Prediction Center. They issue warnings and alerts when a significant event is headed our way. The warning time depends on how fast the CME is traveling. Typical CMEs travel at a few hundred kilometers per second. They take 2 to 3 days to reach Earth. That gives us 2 to 3 days warning. Fast CMEs can travel at over 1,000 kilometers per second. They reach Earth in less than a day. The fastest ever recorded, the one from July 2012 that missed us, traveled at about 3,000 kilometers per second. It reached the orbit of Earth in just 17 hours. If it had been aimed at us, we would have had less than a day to prepare. Still, 17 hours is better than nothing. It's better than being hit with no warning at all. But it's not much time. Certainly not enough to implement major protections or evacuations. The warnings are only as good as our ability to act on them. If we get a warning that a major storm is coming, what do we actually do? Individuals can't do much. You can't protect your home against geomagnetic currents. You can prepare like you would for any power outage. Stock up on food and water. Fill your car with gas. Charge batteries. Withdraw some cash. But that's about it. The real response has to come from utilities and governments. Power companies need to prepare their grids, shut down vulnerable transformers, reroute power through less vulnerable paths, reduce load to minimize stress on the system. Satellite operators need to put satellites in safe mode. Airlines need to reroute or ground flights. All of this requires coordination and quick decision-making, and it's not clear we're set up to do that effectively. There are also protection measures that can be implemented in advance, before a storm hits. Hardening infrastructure to withstand geomagnetic storms. For the power grid, this means installing devices called blocking capacitors at key points. These block direct current, the type of current induced by geomagnetic storms, while allowing alternating current, the normal grid current, to pass through. They're expensive, millions of dollars per device, and you need them at multiple points throughout the grid. But they work. They can dramatically reduce the risk of transformer damage. Some utilities have installed them, others haven't. It comes down to cost versus risk. If your utility thinks the risk is low or distant, they might not invest in protection. If they've experienced problems in the past, or if regulators require it, they might. It's inconsistent. Satellites can be hardened against radiation. Military and critical scientific satellites have extensive radiation shielding and redundant systems. They're designed to survive in the harsh space environment, but they're also much more expensive. A hardened satellite might cost twice as much as a standard commercial satellite. For military applications, that's acceptable. For commercial applications, companies look at the trade-off. How much more does hardening cost? What's the probability of a damaging storm during the satellite's operational life? If the probability is low and the cost is high, they might take the risk. Launch a cheaper, less protected satellite. Hope it survives. If it doesn't, launch a replacement. This calculus works for companies, but it means our satellite infrastructure as a whole is vulnerable. Many satellites lack adequate protection. A Carrington-level event would knock out a significant fraction of them. The ones that survive would be overwhelmed trying to provide services normally handled by the larger constellation. There's also personal preparation you can do. Thinking about worst-case scenarios is uncomfortable. Most people don't want to imagine the power being out for months. It's depressing, scary, easier to assume it won't happen or that someone will fix it quickly if it does. But hope is not a strategy. If you understand the risk, you can take steps to be more resilient, not to survive some apocalyptic collapse, though that's possible, but to be comfortable and safe during an extended power outage, to have what you need without depending on functioning infrastructure. This isn't about becoming a survivalist. It's about prudent preparation for a known risk. Start with the basics, food and water. You should have at least 2 weeks' worth of non-perishable food stored, canned goods, dried foods, things that don't require refrigeration or cooking. You can survive on cold food if you have to. Water is more critical. You need about 1 gallon per person per day for drinking and basic sanitation. 2 weeks' supply is 14 gallons per person. That's a lot of water. Heavy and bulky, but necessary. You can store it in large containers, or have a way to purify water from local sources. Filters, purification tablets, boiling if you have a way to make fire. Think through your water needs and have a plan. Heat and light. If it's cold, you need a way to stay warm. Blankets, warm clothes. If you have a fireplace or wood stove, stock firewood. If not, consider a portable heater that doesn't require electricity. Propane heaters, kerosene heaters. They produce carbon monoxide, so you need ventilation, but they can keep you alive in freezing temperatures. For light, have flashlights and batteries. Candles, solar, powered lights. You don't need to light your whole house, just enough to see what you're doing, read, move around safely at night. Communication. If the power is out, cell phones probably won't work. Cell towers need power. Even if your phone is charged, it can't connect to a network. Have a battery-powered or hand-crank radio. AM and FM stations might still be broadcasting if they have backup power. Emergency broadcasts will tell you what's happening and what to do. This is critical. In a crisis, information is as important as food and water. Knowing what's going on helps you make better decisions, reduces panic, gives you something to do besides worry. Medical supplies. If you take medications, have extras, at least a month supply, more if possible. Talk to your doctor about this. Explain you want to be prepared for emergencies. Most will understand and prescribe extra refills. Have a first aid kit, bandages, antiseptic, pain relievers, basic medical supplies to treat minor injuries and illnesses. If someone in your family has special medical needs like diabetes or heart conditions, think through what they'll need if regular medical care isn't available. It's grim to consider, but necessary. You can't rely on hospitals being functional during a major grid down event. Cash. Keep some cash on hand. If electronic payment systems are down, cash is the only way to buy things. People might not accept it because they can't verify its value without functioning systems. But it's better than nothing. A few $100s, small bills, 1s, 5s, 10s. Easy to make change. This isn't about hoarding wealth. It's about having the ability to make transactions if you need to. Community. Talk to your neighbors. Get to know them before an emergency. In a crisis, communities that work together fare better than individuals acting alone. You can share resources, share skills, watch out for each other, provide security. A strong community is more resilient than isolated individuals. This takes time to build. You can't create community trust in the middle of a disaster. It has to exist beforehand. So invest in your community now. Be friendly, be helpful, build relationships. This is good advice in general. It also makes you safer in emergencies. None of this guarantees survival. If things get bad enough, preparation only goes so far, but it increases your odds. It gives you options. It reduces panic because you have a plan. You know what to do. You're not scrambling in the moment, trying to figure out how to feed your family or stay warm. You've thought it through. You have supplies. You're as ready as you can be. That's all anyone can do. Prepare and hope it's not needed. Now, let's talk about worst-case scenarios. What happens if a Carrington-level event hits today and we're not ready? What does the world look like in the hours, days, weeks, and months after? Let's walk through it. The event begins with a massive solar flare. Astronomers see it happen. Within minutes, warnings are issued. A large CME has been ejected toward Earth. Based on its speed and direction, impact is expected in 17 hours. Governments are notified. Utilities are alerted. The media reports it, but most people don't fully understand what it means. It sounds abstract. A solar storm. So what? We've had those before. Life continued normally. This will be the same. Most people go about their day. They go to work. They make plans for the evening. They assume tomorrow will be like today. Utilities try to prepare. They shut down what they can. They reduce load on the grid. But there's only so much you can do in 17 hours. The grid is complex. You can't just flip a switch. You have to do it carefully, or you cause blackouts trying to prevent blackouts. So they do what they can. Some transformers are taken offline. Some transmission lines are disconnected. But most of the grid stays operational. People need power. Hospitals need power. You can't shut down everything based on a forecast that might be wrong. So the grid stays up and vulnerable. 17 hours pass. The CME hits. Earth's magnetosphere compresses. Geomagnetically induced currents surge through power lines. Transformers overload. Some shut down safely, others don't. They overheat. Internal components melt. They fail catastrophically. The grid starts to collapse, first in one region, then another, cascading failures as intact parts of the grid try to compensate for failed parts and overload. Within minutes, vast regions are without power, hundreds of millions of people. The lights go out, appliances stop, computers go dark. People look around confused. Another power outage. They wait for it to come back on. But it doesn't. Minutes pass, then hours. People start to realize this is different. This is bigger. This might not be fixed quickly. Satellites in orbit are bombarded with radiation. Some systems fail. GPS signals become unreliable. Communications satellites go offline. The internet starts to fragment as parts of the infrastructure fail. International connections go down first. Undersea cable landing stations lose power, then regional connections, then local. Within hours, large parts of the internet are inaccessible. People can't get online, can't check news, can't communicate with distant friends or family. They're isolated. The information flow stops. Rumors spread. Misinformation fills the void. No one knows what's really happening or how bad it is. Planes in the air lose navigation and communication. Some declare emergencies and land at the nearest airport. Others continue flying, hoping their destination airport is still operational. Some aren't. Pilots find darkened runways. No lights, no communication from the tower. They have to make judgment calls. Circle and hope the power comes back. Divert to another airport. Land anyway in the dark. Some choose one option, some another. A few crashes occur. Not many. Pilots are skilled and planes have backup systems. But some. Enough that it's clear this is a disaster. Airports shut down. All flights grounded until the situation is resolved. The first day is confusion and disbelief. People expect the power to come back. It always has before. Utilities issue statements saying they're working on it. Give us time. We'll have it fixed soon. But they're lying or deluded. They don't have it fixed. They can't get it fixed. Transformers are destroyed, hundreds of them. Each one takes months to replace. The grid is down and will stay down. But no one wants to admit that yet. Not to the public, maybe not even to themselves. The second day, reality sets in. The power is not coming back quickly. Stores are being emptied. People are hoarding. Fights break out. Police try to maintain order, but they're overwhelmed. Some stores close to protect their employees. Others stay open and raise prices. Price gouging during an emergency. It's illegal, but who's enforcing? The government has bigger problems. Food distribution breaks down. Trucks can't fuel up. Drivers don't show up for work. They're home protecting their families. Shelves stay empty. People who didn't prepare start to panic. By the end of the first week, the full scope is clear. This is not a temporary outage. This is long-term. Maybe months, maybe longer. Water stops flowing in cities. Pumps need electricity. People are told to boil water if they have any, but most don't have a way to boil without electricity or gas. They drink whatever they can find. Disease spreads. Hospitals are overwhelmed, operating on generators that are running out of fuel, making impossible choices about who to treat. Death toll rises, not from the storm itself, but from the infrastructure collapse. Violence increases, looting, theft, people desperate for food and supplies. Police can't respond everywhere. Some areas descend into chaos. Others organize. Neighborhoods form watches, defend their communities, share resources. It's uneven. Some places hold together. Others fall apart. The social fabric of civilization is tested, and in many places, it tears. After a month, millions have died. Starvation, disease, violence, lack of medical care. The elderly and sick die first, then the young, then anyone without resources or community. It's a slow-motion catastrophe. Every day, more people die. Bodies pile up because there's no way to dispose of them properly. This creates more disease. The death toll accelerates. By 3 months, the toll might be in the tens of millions globally, not evenly distributed. Urban areas suffer most. Rural areas with local food and water fare better, but no one is unaffected. Recovery begins slowly. Transformers are manufactured and shipped. Power is restored section by section. Critical areas first. Hospitals, water treatment plants, distribution centers, then residential areas. It takes years. The economy is devastated. GDP has collapsed. Unemployment is extreme. Many businesses have failed, will never reopen. The world after is different from the world before. Poorer, smaller, more fragile. People who lived through it are traumatized. Society is changed permanently. This is the nightmare. The worst case, it might not be this bad. Maybe we get lucky. Maybe the storm is weaker than feared. Maybe our protections work better than expected. Maybe people come together instead of falling apart. Maybe the death toll is lower, but it could be this bad. It could even be worse. And the terrifying thing is that we know it's possible. We know the threat exists, and we're not doing enough to prevent it. We're gambling that it won't happen during our lifetimes, that someone else will deal with it, that technology will save us somehow. It's a dangerous gamble, one we might lose. So what can you do? On an individual level, prepare as described earlier. Have supplies, have plans, be ready for an extended emergency, but also understand the bigger picture. Be aware of this threat. Talk about it. Demand action from leaders and utilities. Space weather protection is not expensive compared to the cost of a disaster. Hardening the power grid would cost billions globally, but the economic damage from a Carrington event would be in the tens of trillions. It's a good investment, a very good investment, but it requires political will. It requires people demanding action, and that only happens if people understand the threat. Write to your elected representatives. Tell them space weather protection should be a priority. Support policies that mandate grid hardening, that incentivize satellite hardening, that fund space weather research and forecasting. Be the voice that says this matters. This is not some distant hypothetical. This is a real threat with real consequences. And we need to take it seriously before disaster strikes, because after disaster strikes, it's too late. We'll be dealing with the aftermath instead of prevention. Let's dig deeper into personal preparation and what it really means to be ready for an extended grid down scenario. When we talk about preparation, most people think about storing food and water. That's important, but there's so much more to consider. Your entire way of life changes without electricity. Things you take for granted become difficult or impossible. Refrigeration. You can't keep food cold. Anything perishable spoils within days. Meat, dairy, vegetables, all of it goes bad. You're left with canned goods, dried foods, things that don't need refrigeration. This works, but it's monotonous, and it requires you to have thought ahead and stocked up. Most people don't have more than a few days of food in their homes. They shop frequently, buying fresh food for immediate consumption. This works wonderfully when stores are restocked constantly. It fails completely when the supply chain breaks. Cooking becomes a challenge without electricity. If you have a gas stove and the gas is still flowing, you're lucky. But gas distribution requires electricity for pumps and control systems. If the power is out long enough, gas stops flowing too. Then you need alternatives. Camp stoves, propane, charcoal, wood fires. Each has drawbacks. Camp stoves need fuel. Propane cylinders run out. Charcoal produces dangerous fumes if used indoors. Wood fires are smoky and hard to control, but they're better than nothing. You can cook. You can boil water. You can stay alive. The key is having equipment and fuel before you need it. During a crisis, stores empty immediately. You can't buy what you need because everyone else is trying to buy the same thing. Sanitation becomes a serious issue. Toilets need water. If your water isn't running, toilets don't flush. This gets unpleasant fast. A family of 4 might need to flush 10 or 15 times per day. That's a lot of water. If you don't have running water, you need an alternative. Bucket toilets, outhouses, digging cat holes in the yard. These work, but they're gross and potentially dangerous. Human waste carries disease. Cholera, typhoid, dysentery. If waste isn't handled properly, disease spreads. This is why sanitation infrastructure is so important. It's not just convenience, it's public health. Remove that infrastructure and disease becomes a major threat, especially in cities where population density is high and people are living close together. Washing becomes difficult. Without running water, you can't shower, you can't wash dishes properly, you can't wash clothes in a machine. Everything has to be done manually with whatever water you can gather. This takes time and effort. It's exhausting. And if water is scarce, you have to prioritize. Drinking water first, cooking second, washing last. People start to smell. Hygiene suffers. This contributes to disease, skin infections, respiratory infections, all more common when people can't stay clean. Personal hygiene items become valuable. Soap, toothpaste, toilet paper. These seem trivial until you don't have them. Then they're luxuries. Think about having none of these things for months. It's degrading. It's uncomfortable. It's another way that modern life unravels without the infrastructure we depend on. Security is another major concern. In normal times, we rely on police to maintain order. They patrol, they respond to calls, they investigate crimes. This system works because police are mobile, organized, and have tools like phones and radios to coordinate. Without electricity, that system breaks down. Police can't respond quickly, they can't coordinate. They're limited to what they can do locally on foot or with limited fuel for vehicles. Criminals know this. If you're inclined to take advantage, a grid-down situation is an opportunity. Homes can be broken into with less risk of police response. Stores can be looted. People can be robbed. The normal deterrents are weakened. This means individuals and communities need to provide their own security. Neighborhood watches, armed patrols, visible deterrents. This works if communities are organized and cooperative, if neighbors trust each other and work together. But in many places, that trust doesn't exist. People don't know their neighbors. Communities are fragmented. In those places, it's every family for themselves. You protect your home. You stay inside. You don't trust outsiders. This isolation makes everyone more vulnerable. Strength comes from cooperation, but cooperation requires social capital, relationships built over time. You can't create that overnight. If you want your community to hold together in a crisis, you need to invest in it before the crisis. Be a good neighbor. Participate in community events. Build relationships. This pays dividends when things go wrong. There's also the psychological toll to consider. Extended emergencies are stressful. Uncertainty, fear, grief if you've lost loved ones, boredom and frustration from not being able to do normal activities. Humans are social creatures. We're accustomed to entertainment, television, internet, social media, books, hobbies. All of that might be unavailable or limited. Long, dark evenings with nothing to do, no way to distract yourself from worry. This is when mental health suffers. Depression, anxiety, PTSD. These are real issues in disaster scenarios, and there's no treatment available if the medical system has collapsed. People cope as best they can. Some adapt, others don't. Communities that can provide support, where people can talk and share burdens, do better. Isolated individuals struggle more. Mental health matters. It affects decision-making, cooperation, survival. Taking care of mental health is as important as physical health. Children are particularly vulnerable psychologically. They don't understand what's happening. They're scared. Their routine is disrupted. They can't go to school, can't see friends, can't play as they normally would. Parents have to provide security and normalcy as best they can. Tell stories, play games, keep children occupied and reassured. This is hard when you're stressed yourself, when you're worried about where the next meal comes from. But children need it. They need to feel safe, need to believe adults have things under control even when we don't. This puts enormous pressure on parents, and some crack under that pressure. They can't maintain the facade. Children see the fear and absorb it. This creates long-term trauma. Children who live through extended disasters often have psychological scars that last into adulthood. Anxiety, trust issues, difficulty forming relationships. The impacts are profound. Let's also discuss the long-term recovery process in more detail. Even after power is restored, which could take years, the world doesn't just snap back to normal. Infrastructure is damaged beyond just the power grid. Roads have deteriorated without maintenance. Bridges have become unsafe. Water systems need extensive repairs. Telecommunications networks need rebuilding. All of this takes time and money, and the economy is in shambles. GDP has collapsed. Tax revenues are down. Governments are broke or deeply in debt from emergency spending. Where does the money come from for reconstruction? Debt, borrowing from other countries or international organizations. But that debt has to be paid back. It means austerity, reduced services, higher taxes, economic pain that lasts for decades. Businesses that failed during the crisis don't come back. Jobs are lost permanently. Unemployment stays high for years. This creates social problems. Crime increases. Poverty increases. People struggle to find work. Young people entering the job market face limited opportunities. A lost generation economically. This happened in some countries after the 2008 financial crisis. It could happen globally after a Carrington event. The economic recovery would be slow and painful. Living standards would be lower for decades. Wealth accumulated before the crisis would be lost. Retirement savings wiped out. Real estate values crashed. It would fundamentally reshape society. The rich become less rich. The middle class shrinks. Poverty expands. Inequality might increase as those with resources can weather the crisis better than those without. Political consequences would be significant too. Governments that fail to protect their populations or respond effectively to the crisis face backlash. Leaders are voted out or overthrown. New movements arise promising solutions. Some democratic, some authoritarian. Crisis creates opportunity for political change. Not always good change. Desperate people support desperate measures. If a strong man promises order and security, people might support him even if it means giving up freedoms. We've seen this pattern throughout history. Economic crisis leads to political instability, which leads to authoritarianism. It could happen again after a major solar storm if the response is bungled. International relations would also shift. Countries that recover faster gain advantages. Countries that can help others gain influence. China might recover faster than the United States if it has better infrastructure protection or can mobilize resources more effectively. This could shift the global balance of power. The United States has been dominant since World War II. A Carrington event could end that dominance if America is hit harder than its competitors, or if America recovers slower. Geopolitical alignments could realign. New alliances form. Old alliances break. The world order we've lived under for decades could change fundamentally, all because of a solar storm, a natural disaster with cascading consequences that ripple through every aspect of society. There's also the question of how climate change interacts with solar storm risk. This might seem unrelated, but they're connected. Climate change is making our power grids more vulnerable even before solar storms are considered. Extreme weather events, heat waves strain grids as everyone runs air conditioning. Wildfires damage transmission lines. Hurricanes knock out power for weeks. The grid is increasingly stressed. It's operating closer to capacity. It has less margin for error. If a solar storm hits when the grid is already stressed from extreme weather, the combined impact could be worse than either alone. This is a known problem. Climate adaptation planning and space weather protection need to be coordinated. We need grids that can handle both challenges. Currently, most planning treats them separately. That's a mistake. They interact. We need integrated solutions. Another interaction is with other technologies we're developing: electric vehicles, solar panels, battery storage. These are supposed to help with climate change by reducing fossil fuel use, but they add complexity to the grid. Electric vehicles charging create new demand patterns. Solar panels create variable supply that needs to be balanced. Battery systems need sophisticated control. All of this requires more electronics, more sensors, more computers, all potentially vulnerable to solar storms. As we electrify more of our economy to fight climate change, we increase our vulnerability to space weather. This isn't an argument against electrification, it's an argument for building resilient electrical systems. Systems that can handle solar storms and other disruptions. We need both clean energy and robust energy. Those goals are compatible, but they require intentional design. Let's talk about technological solutions being developed. Scientists and engineers are working on better ways to protect infrastructure. Advanced materials that can shield electronics from radiation. Better transformer designs that can handle geomagnetic currents. Smart grid technologies that can isolate problems and reroute power automatically. These are promising, but they're still in development or deployment. They're not everywhere yet, and some might not work as well as hoped until tested under real conditions. Real solar storms. We won't know for sure until the next big one hits. That's the nature of preparing for rare events. You design solutions based on models and simulations, but reality might differ. Something you didn't anticipate, some failure mode you didn't predict. Engineers do their best, but nature is tricky. It finds weaknesses. There's also research into forecasting, better models of the sun, better understanding of how CMEs form and propagate. Machine learning applied to solar data, looking for patterns that precede eruptions. The goal is to extend warning time. If we could predict a Carrington-level event days or weeks in advance instead of hours, we could do so much more. Manufacture and pre-position equipment, evacuate vulnerable populations, stockpile supplies, coordinate international responses. More warning time means more options. It's the difference between reacting in panic and responding strategically. Scientists are making progress, but the sun is complex. Predicting specific eruptions far in advance is still beyond our capabilities. Maybe it will always be. Maybe there's inherent unpredictability in solar physics. Chaos theory suggests that complex systems can't be predicted accurately far into the future. We might hit a ceiling on how much advance warning is possible. Regarding international cooperation, there are efforts to coordinate space weather responses globally. The United Nations Committee on the Peaceful Uses of Outer Space has working groups on space weather. Countries share data. They develop common standards. They plan coordinated responses. This is good. It's progress. But coordination is hard. Countries have different priorities and capabilities. Wealthy countries can afford protection, poor countries can't. And, in a crisis, national interests might override cooperation. Countries might hoard resources, close borders, protect themselves first. International agreements work until they don't, until the crisis is severe enough that self-preservation kicks in. We saw this during COVID. Initial cooperation, but then countries acting independently, closing borders, restricting exports of medical supplies. It's human nature. We cooperate until we feel threatened. Then we retreat into tribalism, nations, communities, families, protecting our own. This tendency could undermine international responses to a solar storm. We need to plan for that, build systems that work even if cooperation breaks down. There's also the cultural dimension. Different cultures respond to crises differently. Some emphasize community and collective action. Others emphasize individual responsibility. Some trust government to take the lead. Others distrust government and want to handle things locally. These cultural differences affect how societies respond to disasters. No one approach is universally better. Each has strengths and weaknesses, but it means responses will vary. What works in Japan might not work in the United States. What works in Germany might not work in Brazil. We need flexible approaches, room for cultural adaptation. Imposing one-size-fits-all solutions won't work. Local solutions informed by local knowledge and values. This makes coordination harder, but it respects human diversity, and it might lead to better outcomes because people are more likely to follow plans they believe in and that fit their cultural context. Finally, let's address the spiritual and philosophical dimensions. A Carrington event would force us to confront our relationship with nature and technology. We've become so dependent on technology that we've forgotten how vulnerable we are. Nature can humble us anytime. Solar storms, earthquakes, volcanoes, pandemics. We've created the illusion of control, the illusion that we've tamed nature and don't need to worry about it anymore. A major solar storm would shatter that illusion. It would remind us that we live on a planet orbiting a star, both subject to forces we don't control and barely understand. This could be a healthy reminder, a recalibration of our relationship with the natural world. Or it could be traumatic, a loss of faith in progress and technology. Different people would respond differently, but collectively, society would change. We'd be more cautious, more humble, more aware of our limits. One last thing to consider is the opportunity that crisis presents. Yes, a Carrington event would be catastrophic, but it would also force changes that might be beneficial long-term. Our current infrastructure is aging. Much of it was built decades ago and needs replacement anyway. Power grids, water systems, telecommunications, all overdue for upgrades. A solar storm that destroys old infrastructure creates an opportunity to rebuild better. Smarter grids, distributed generation, renewable energy, systems designed from the ground up to be resilient. This is expensive. Too expensive to do proactively when the old systems still work. But after a disaster, the money becomes available. Government spending, insurance payouts, international aid. Reconstruction happens, and if done wisely, we emerge with better infrastructure than we had before. The same applies to social systems. Communities that come together during crisis often stay closer afterward. People who helped each other remember. They maintain relationships. They cooperate more in normal times. Disasters can strengthen social bonds. Not always. Sometimes they fracture communities, but often they bring out the best in people. Kindness, generosity, cooperation. These pro-social behaviors get reinforced. Society might emerge more cohesive, less atomized, more resilient not just to future disasters, but to everyday challenges. This is the silver lining, the possibility that something good comes from catastrophe. It doesn't justify the suffering, but it offers hope that we can recover and possibly thrive. Thank you for exploring this threat with me. If this changed how you think about our technological vulnerability, a like or subscribe really helps the channel keep investigating these crucial topics. And remember, we're living on a planet orbiting a star that occasionally throws tantrums. Those tantrums used to be harmless, but we've built a civilization that's exquisitely vulnerable to them. We've placed all our eggs in an electromagnetic basket, and we're not protecting that basket nearly well enough. The threat is real, the consequences are severe, but solutions exist if we have the wisdom to implement them. Stay aware, stay prepared, and let's hope that when the next big one comes, we're ready. Good night, and may the sun stay calm.